Enthalpy and entropy are related to a term called Gibbs free energy, which we denote by the letter G. And this is the amount of work energy that can be done by a chemical reaction that is at constant temperature and constant pressure. Now, this is often referred to as chemical potential because it's similar to the idea of potential energy in a mechanical system. So our chemical reaction is the change in Gibbs free energy is equal to the entropy or enthalpy times the temperature times the entropy, change in entropy. And so because entropy helps us decide if something is spontaneous, Gibbs free energy also helps us to decide. But because there is a negative sign in front of the entropy, that means that the Gibbs free energy has the opposite sign when it is spontaneous. So positive for the entropy when it's spontaneous, but it's negative for the delta G for a spontaneous reaction. So we know that a process is spontaneous when delta G is negative. Let's look at our equation and see some different cases. So let's start with a negative delta H minus our temperature, and we're going to look at a positive entropy. So if we have a positive entropy times with this negative sign in front of it, that is going to be negative. Our delta H is negative, and so in this case, our delta G, no matter what the temperature is negative, and our reaction will be spontaneous. Okay. How about if we have a positive delta H and a negative entropy? Okay, so what does positive delta H mean again? Well, positive delta H means it's endothermic, right? It's absorbing heat from the surroundings. So we have a positive delta H, a negative entropy. So this is going to be positive. We've got a negative S with a negative sign in front of that. So that is going to be positive. That means in all cases, no matter what the temperature, our delta G is going to be positive. And that means that it's going to be non-spontaneous under all conditions and all temperatures. Okay, so now let's look at the case where we have a negative delta H and we have a negative entropy. Okay, so if the temperature is low, if the value is small, that means that our S is going to be small compared to our delta H. In that case, if we're at a low temperature, oops, that means our delta G is negative and it's spontaneous. Okay. How about if we have a high temperature? Okay, well, high temperature means that the value of the temperature times the entropy is going to be large. It's going to be bigger than our delta H. And so because the negative and the negative becomes positive, that means that at high temperatures, we have a positive delta G and it's non-spontaneous. Okay. So we've got one more example to look at. What if we have a positive delta H, which means it's endothermic. We have a positive entropy, so it's getting more disordered. And now let's look at our signs. Let's say we're at low temperature. Okay, so low temperature, our T is going to be small. It's going to make our T times delta S small. But if that is smaller than our delta H, that makes the delta G positive, which means that it's non-spontaneous. Okay. All right, what if we're at high temperature? Okay, well, at high temperature, the T becomes large. We're going to have a larger negative value for the temperature times the entropy. It's going to be larger than our delta H. And so in that case, our delta G is going to be negative and it's going to be spontaneous at high temperatures. So it's really important to look at the different signs on our entropy and our enthalpy in order to determine our Gibbs free energy. Now, if Gibbs free energy is exactly 0, that means that our equilibrium, or our reaction is at equilibrium. Okay, so if we think about our chemical reaction, at equilibrium, our delta G is equal to 0. If we're not at equilibrium, we're going to be moving towards that equilibrium position. So it's going to be spontaneous if we're moving away from pure reactants. It's going to be spontaneous in the forward direction. If we're moving away from pure products towards equilibrium, it's going to be spontaneous in the reverse direction. And if delta G equals 0, that means we're at equilibrium. All right, so here we have a reaction. We have a positive enthalpy in kilojoules and a positive entropy in joules per Kelvin. And so in this case, it depends on the temperature whether or not it is spontaneous. So because our units for entropy are per Kelvin, we do need to convert our units. So we need to go from degrees Celsius to Kelvin. So we have to add 273. And so our temperature that we're going to be working with is 298. The other thing we want to look at is our units. So our entropy has units of joules, our enthalpy has units of kilojoules. We want to make sure those units are the same. And so we need to do a conversion real quick. So we got 95.7 kilojoules. We know there's 1 kilojoule is 1,000 joules. So it would be 95,700 joules. So now we can look at our equation. And plug in our values. So we got 95,700 joules for our enthalpy minus 298 Kelvin times 142.2 joules per Kelvin. And we end up with a value of positive 53,300 joules if we're keeping our significant figures. So what does this mean? This means that because we ended up with a positive value, this is not spontaneous at this temperature. If we wanted to make this spontaneous, our temperature would have to get much larger so that we could overcome that positive value for our enthalpy. All right, so here's a practice for you. Pause the video and see if you can determine if this is a spontaneous reaction or not. Again, we're going to have to do some conversions. So we want to find our temperature in Kelvin. Which is going to be equal to 298. We also need to convert our units, as we have kilojoules and joules. So we end up with negative 847,600 joules. We can plug that into our equation. And again, because they're both negative, this is a case where it depends on the temperature whether it's spontaneous or not. So we have to do the calculation. So our enthalpy is pretty large in this case. Negative 847,600 joules. 298 Kelvin times our entropy, joules per Kelvin. And so in this case, we end up with negative 8.353 times 10 to the 5th joules. Because it's negative, this is a spontaneous reaction. Let's look at that first example that we looked at, where we want to figure out what the temperature is where it becomes spontaneous. So we've already converted our units. We know that it's 95,700 joules because this is the exact same problem as the example we just previously looked at. Our delta G, which we know is equal to delta H minus T delta S. We know that becomes spontaneous when it's negative, so this value has to be less than 0. So now we can plug in our values and solve for T when that delta G is less than 0. Okay. So we're going to move the negative delta T to the other side of our equality. So that should be joules. Okay, we can divide by our entropy. Our joules will cancel, and we will get 673 Kelvin less than our temperature. So this means that the temperature needs to be higher than 673 Kelvin for the reaction to be spontaneous. Calculate the maximum temperature for which this chemical reaction will be spontaneous. Pause the video and give it a try. We've already calculated our delta H in joules previously. So it would be negative 847,600 joules. So now we can look at our equation for delta G. And we know that for it to be non-spontaneous, that delta G has to be a positive value. So we can plug in our values, negative 847,600 joules minus the temperature we're trying to solve for times our entropy, which is negative 41.3 joules per Kelvin. We're going to move that minus T times our entropy to the other side of the equation. And we're going to divide both sides by the entropy. Doing that, we come up with 20,523 Kelvin. And if we want to find this in degrees Celsius, we can subtract 273 from this temperature. It wasn't asked for you to do this in the problem, but just in case you wanted to see what the temperature was in Celsius, 20,250 degrees Celsius. So any temperature above this will make the reaction non-spontaneous.